If you look at the architecture of almost any modern large language model, beneath the billions of parameters and the massive clusters of GPUs, the actual flow of information relies on a surprisingly simple geometric trick: the residual connection. You're likely familiar with the formula: x sub L plus 1 equals x sub L plus f of x sub L. Think of that straight line as an identity highway. It allows deep networks to train by giving information a clear, uncorrupted path forward and, crucially, giving gradients a direct path backward. But as we scale to massive models, this single highway becomes a severe bottleneck. A single embedding vector has to simultaneously hold syntax, local context, and multiple competing semantic interpretations. Say, bank as a river versus bank as a financial institution. To solve this representation bottleneck, researchers introduced hyper-connections, or HC. Instead of one residual stream, imagine expanding the dimension of the residual space. We create n parallel streams. At each layer, we introduce a set of learned matrices. hpre reads information from these parallel streams into the main layer, hres mixes the streams among themselves, and hpost writes the layer's output back into the streams. This gives the network incredible expressive power. It can route different concepts through different lanes without them interfering. But there is a fatal geometric flaw. In a standard residual connection, the identity mapping is guaranteed. X remains X. But in unconstrained hyperconnections, we are multiplying our streams by a dense mixing matrix, hres, at every single layer. From linear algebra, we know what happens when you repeatedly apply linear transformations. If the eigenvalues of this mixing matrix are even slightly greater than 1, the signal explodes. If they are slightly less than 1, the signal vanishes. Over 100 layers, this compounds into absolute numerical chaos. We have sacrificed the identity property for expressiveness. The network becomes incredibly unstable to train, forcing us into a corner where we can't reliably scale to frontier-level depths. This brings us to DeepSeek's paper, Manifold-Constrained Hyper-Connections, or mHC. The core insight here is profound, yet beautifully simple. We don't need to reduce the number of lanes to restore stability. We just need to put mathematical guardrails on how information mixes between them. We need to restore the identity property by projecting the mixing matrix onto a specific, well-behaved geometric space, a manifold. Specifically, the authors constrain the residual mixing matrix, hres, to be a doubly stochastic matrix. What is a doubly stochastic matrix? It's a matrix where all entries are non-negative. Every row sums to exactly 1, and every column sums to exactly 1. The set of all such matrices forms a convex shape in high-dimensional space known as the Birkhoff polytope. Why is this specific manifold the holy grail for our network? Think about the forward pass. If every row sums to 1, the matrix acts as a convex combination. It perfectly conserves the energy or scale of the forward signal. Information is dynamically routed among the lanes, but it can never explode. Now think about the backward pass. Because every column sums to 1, the gradients flowing backward are strictly conserved. We have successfully maintained the perfect, stable flow of a standard ResNet, but with the massive routing capacity of an n-dimensional hyperconnection. To achieve this, the network doesn't magically predict a doubly stochastic matrix out of nowhere. Instead, it outputs a standard, unconstrained matrix of logits. DeepSeek then applies the Sinkhorn-Knopp algorithm. This is an iterative mathematical process that scales the rows, then the columns back and forth. In just a few iterations, it effectively projects the unconstrained matrix onto the Birkhoff polytope. Additionally, they enforce non-negativity on the read and write matrices, hpre and hpost, using functions like sigmoid and softmax. This ensures that when the main layer reads from or writes to the multiple lanes, there is no destructive interference. Now, if you're a systems engineer, your alarm bells are probably ringing. Computing sinkhorn knot projections and managing multiple massive residual streams at every single layer sounds like a memory bandwidth nightmare. You're storing an enormous amount of intermediate activations just to compute the gradients later. A purely mathematical fix is useless if it runs out of memory on your cluster. To make mHC scale, the authors introduced rigorous infrastructure optimization. First, kernel fusion. They wrote custom CUDA kernels that fuse the pre-mapping, post-mapping, and sinkhorn NOP projections into a single operation. The data stays in the ultra-fast SRAM while all the math happens, drastically reducing round trips to the global memory. Second, they implemented an ingenious blockwise activation recomputation. Instead of saving the massive multi-stream states for the backward pass, they only save the input at the start of a block of layers. During backpropagation, they simply recompute the hyperconnections on the fly. By calculating the optimal block size, trading off a tiny amount of extra compute for a massive reduction in memory footprint, they constrained the peak memory overhead of mHC to a negligible fraction. It fits beautifully into modern pipeline parallelism setups like dual pipe. What DeepSeek's mHC paper shows us is a fundamental shift in how we approach the scaling laws of AI. Stability is no longer treated as a side effect that we blindly chase with learning rate warm-ups or massive batch sizes. It becomes an architectural guarantee. By mathematically constraining the geometry of information flow, we can build wider, deeper, and vastly more expressive pathways, ensuring that as models grow, their internal complexity doesn't collapse into noise.